You seeing this? You see it all?
Yeah, we're seeing
Yeah,
it.
All right, cool.
grizzly.
Grizzly, yeah. Yeah, I changed my background if you can't tell because it was something else that I couldn't really show. It's not like that bad, but whatever. Did I just draw or did someone draw? What?
We did this.
You guys are
You
seeing
can
what I'm
draw.
seeing, right? This thing. Yeah, someone else is drawing here.
It's all right.
All right, cool. Yeah, so I'll be running tonight's workshop on stack canaries. I'll be going over what they are, how they work, and how they can be bypassed. I just want to make it clear that I am making the assumption that those following along do have a general understanding of how to exploit buffer overflow vulnerabilities, because that is not going to be the main focus of tonight's workshop. It is just the stack canaries themselves. So what is a stack canary? A stack canary is a random value that we place in between the base pointer and local variables of a function stack and is used to detect whether or not a buffer overflow has occurred. So I've got a little diagram of a stack here. And as I just said before, we can see our stack canary between the base pointer and local variables. And the way that it detects whether or not a buffer overflow has occurred is it checks if this value here has been modified at the end of the function's call. So let's say we're doing some simple buffer overflow challenge, and we have a stack canary in our stack with a value of, let's say, 1, 2, 3, 4. And let's also say that we put in enough padding where our padding is just the repeated character capital A or whatever we want to use for padding. We overflow our buffer up to the return address. So the problem is that in order to fill up the buffer with enough padding to get to the return address is that we also have to overwrite the stack canary. So before the function exits, it's going to see that the stack canary has been modified and the program itself will terminate. I've got a simple program here, which I basically ripped off. Can we get rid of the drawings, please? And it's like somehow, because, thank you. So I basically ripped this program off from Exploiter Education and just changed it up a little bit. So this program and the other programs that I'll be going through tonight, they don't use actual stack canaries, rather they implement them with local variables. This doesn't really make a difference. It's just that I think it's easier to learn about them when you can see them within the actual program. So this simple program here just declares a couple of variables first. The first is our canary, which is placed on the stack, and then our buffer, which we can overflow, which has 64 bytes. We then are prompted to input some data, which will be written to the buffer. And then after that, we are simply told whether or not we have modified the canary. And if we have modified the canary and a stack smashing error is thrown, it'll also show us what our value of the canary was. So I'll just run the program now and put in some input that is less than 64, and we get the output canary is not modified. And that makes sense because we haven't overflowed the buffer, so the canary stays the same. However, if we are to input a string that is greater than 64 bytes, I just need to move it over here. If we input a string which is greater than 64 bytes, we will get a stack smashing detected error. If I just put here, print, what are we? We'll do capital A by 64, 65, and we get stack smashing detected. And we can see that we have written to 1 byte of the stack canary because we have 141, and the ASCII value of 41 is capital A. So the general method for bypassing a stack canary is to construct a payload so that writes to the stack such that the stack canary was never modified or changed. And the only way that you can do this is if you know where exactly in the stack canary lies and what the exact value of the stack canary is. Now, if we go back to our little program here, we know both of these things. We know that the stack canary comes right after the buffer that we are overflowing, and we know that the stack canary is being checked if it's equal to this value here. Just disregard this bit of code here. That's just a crappy bit of coding on my part just to make sure the program works properly. So we know that the stack canary's value is hex 61 through 64. And if we just look at an ASCII table, we can see that the hex values of 61 through 64 is A, B, C, and D. So if we exit this program and instead now run the program again with a new payload, but this time we are going to have some padding just to fill up our buffer, which is going to be, we'll do the capital A again by 64. And then we will add our canary, which is going to be DCBA, and we have it in reverse because we're dealing with little endian. And then after that, I'll just put in some more data, just say C by 8. And this is just to prove that we can write to pass the stack canary on the stack without throwing the stack smashing detected error. So if we do that, we then get the output, canary has not been modified. And this means that we have written to data pass the stack canary without throwing this error. So we have tricked the program into thinking that a buffer overflow has not occurred, because when it checks the stack canary, it can see that it has not been modified, which it really hasn't. So that's the general method for bypassing a stack canary. But in most CTFs that we are dealing with, it's never this simple because, well, for one, we don't really get the value just handed to us. And sometimes we don't know exactly where the stack canary is on the stack, just like that. But there are some other cases where there are other methods to obtain the value of the stack canary. And we're going to go through two methods for doing so in this workshop. And the first is going to be the brute force method. So if we go to brute force, all right, so with brute force, before we actually go into detail as to how the brute force method works, we'll first just look at the vulnerable function that we are going to be exploiting. So this is from Pico CTF 2019. The challenge was called Canary, and it has us trying to brute force a stack canary. So this program is pretty simple. We don't need to be worried about this whole display flag function here, because we aren't going to be worried about properly exploiting this program. It's just the stack canary that we're worried about. So if we check the main function, where are we? Here. There are two functions that we properly care about, or actually care about. The first is the read canary function, and the second is the vuln function. So the read canary function, which is right here, simply opens up a text file called Canary and reads the contents of that canary file into the buffer key, which is of length key len, which is 4. And that's all that read canary does. It just reads the value of the text file and puts it in our key buffer. The second function, which is of main interest to us, is the vuln function. It declares a few variables at first, which is our canary. The second is the buffer, which we are going to be overflowing. And the third is a buffer which is not vulnerable to an overflow itself, but stores the length of the input of our buffer here. It's a bit weird, but you'll see. So in this function, we are first prompted to enter the length of our entry. So we first enter the length, and then after that, we are then prompted to input the actual data. So instead of your usual buffer overflow where it's just some gets function that'll accept data of any size, we first specify the length of our data here, and then we import the actual data here, or rather here and here. And then after that, the function either throws an error because stack smashing has been detected, or we have overwritten the stack canary in an incorrect way, or we get this message, okay, now where's the flag? So I'll just show you this program in action for a bit. If we run this program, we are told to enter the length of our entry. Let's say we just do 4. And we can input 4 A's or just some data, doesn't matter. And we get the message now, okay, now where's the flag? And that program works fine. If we run it again and we'll try and overflow the buffer here, we'll put in an input of 33, and this is because the buff size constant here is 32. So we will overflow the buffer by 1 byte. So if we put in 33, we do need a payload of 33 bytes. So let's do just see print dash a by 33. We get our A's, copy that in, put our input, and we get the stack smashing detected error. Where are we? Let's see. So we overflowed our buffer by 1 byte, and in doing so, we had written to the canary. So now that we know how the program works, we should talk about how the actual brute force method itself works. So if we keep that open, clear this, and get our stack up again, slash explanation slash stack. So the way to brute force a stack canary is not by testing every possible stack canary value as a whole, because that would take far too long. We know that the stack canary is of length 4, and because there are 256 possible values each character could have, we would have to run 256 to the power of 4 iterations at most to get the value of our stack canary. And that's going to take way too long. However, what we can do instead is brute force the stack canary 1 byte at a time. So let's suppose I have 4 A's right here, and these A's are meant to represent the padding required to just fill up the buffer but not overflow it. And let's say that we know the stack canary of our vulnerable program, and let's just say it's 4, 5, 6, 7. So what we could do is we could input a payload of size 5, which fills up our buffer and then includes just 1 character, let's say 0, right? And if we are to send this payload, the program would throw a stack smashing error. So we know that the character 0 is not part of the stack canary. We could try 1, we'll get the same error, 2, 3, but now with 4, the program will no longer throw an error because we've only overwritten the first byte of the stack canary, and it's just so happens that this character is the correct first character of the stack canary. So the stack canary itself as a whole still appears to be unmodified. So that means that we know that 4 is the first character of the stack canary. And what we can do then is just repeat the process. Now that we know the first character, we start brute forcing the next one. 0, 1, 2, 3, 4, and 5. And so on until we get our full stack canary. So that is the general method for brute forcing a stack canary. But obviously we don't want to do that manually, so we should write a program to do it instead. So I have a proof of concept Python script which is going to interact with our vulnerable program here. And so the way it works is it declares an object, or variable I should say rather, that points to our vulnerable binary, and then another variable which opens a process for that binary. And what it does is it reads the output of that program until we are prompted to input the length of our data, which is put in the vulnerable buffer. We then send some length, whatever we want to. In this case, it'll be 33. And then after that, we read the output of the program again until we are prompted to input the actual data of our program. We then send our actual data to the program. And then this last line here just prints out the rest of the output in the program. So if I were to run this proof of concept right now, there are a few things here which aren't too important for our purposes. This doesn't matter too much. We are prompted to input the length of our entry. We do so even though we can't see it here, and same with the actual data that we input. And we then get to read the final message of the program, which is that we caused a stack smashing error, and that is true because we inputted a data of the size 33, and that much data was accepted. So I've seen enough live demos fail that it's probably going to happen to me too, but if I fail in writing this exploit to brute force the stack canary, I have already written one right here, so we can go through that if I mess up that bad. So we'll make a file called leak.py, and we'll first import Prone Tools as we need that to work with this program. There are a few variables we want to declare. I think the first is going to be count, and this is simply going to refer to which character we are iterating over from 0 to the 0th to the 255th character for each byte. The next variable would just be our padding count, so just 32. I just don't want to hard code 32 to fill up our buffer. The next is our canary, which currently is just the empty string because we don't know what it is. And the final variable will be the binary which we are going to be running, which is our vulnerable program. And then we have to just put in this line. Disregard this, it's not important. It's just to not log a bunch of stuff that we don't want to be seeing when this program runs. Login.error, cool. So the general logic of this program needs to be, we need to keep looping until the canary is of length 4, because once the canary is of length 4, then we know that we have our full stack canary. And while that is not the case, we need to add a new candidate character to our current canary, and then and then go through the vulnerable program and try input our padding plus that candidate canary. And if the program throws an error, then we know that particular character is not part of the canary. And if it doesn't throw an error, then it must be. And so we can then reset the process, but now with the next character. So we'll do while the length of our canary is less than 4. We will let our canary equal itself plus our candidate character, which will be character count. It's just the character function just outputs the nth hex character. So 0 would be 0, 0, and then 0, 1, and so on, up to FF. We'll just print the canary out for the sake of debugging purposes. We will also begin our process of our binary. So bin.path. And similar to our proof of concept, which we will look at again, we will read the output of our program until we are prompted to input the length of our payload. And once we are prompted, we will send the actual length, and the length will be our padding plus the length of our canary, our current candidate canary, that is. And that looks about right. We will then continue to read the output of our program until we are prompted to input the actual data of our, the actual data being put into our vulnerable buffer. And then once we are prompted, we will send our data, which is going to be our padding character, which is A, or whatever, it doesn't really matter, by our padding. And we will add the canary, our candidate canary, onto the end of that. We will then store the final output of the program in the, the output of the program in the variable output, so receive all. And then we need to check whether or not this particular candidate canary didn't throw an error, or if it did. Now we know that, I'll get out of this one. Now we know that that if we print out the message, okay, and now where's the flag, that we didn't modify the stack canary in an illegal way, I guess we'd say. So we could just we could just say, well, if okay is in output, then we know that our candidate canary must be valid. And so we can just reset the count back to 0 so that we reset the process, but now on the next character of the canary. Otherwise, if that is not the case, we need to get rid of the character that we just added on to the canary. So we'll let it equal itself, but from itself up to its last character. And we also need to increment the count by 1, plus equals 1. And if I've written this program correctly, we will have our stack canary by the end of the loop. Stack canary plus canary. I'll just take a look at that for a second. If any of you see anything wrong with that, like as far as just syntax goes or any logic, shout it out. I think that's fine. Yeah, we'll try run that. So hopefully if we run this program, and that's looking pretty good so far. And so we do get our stack canary, which is capital N, lower N, capital S, and lower C. And just to prove that this actually is our stack canary, we'll do the same thing as we did in our previous vulnerable program, which is we will now make a payload which writes to the stack past the stack canary, but we'll make sure that it doesn't throw the stack smashing detected error. Where were we? We had our stack canary and we wanted to write to data past the stack canary on the stack. So we can now construct a payload which will do that. So we'll say python-c will print our padding to fill up the buffer, which will be A by 32. We'll add our canary, which is M and SC, and we'll then add our data, which is to be written past the stack, just to show that it's actually working. I'll just C by 8, and that's our payload right there. So if we are to now run this vulnerable program again, and we'll input a length of 60 because I can't count, and put in this payload here, we now get the message, okay, now where's the flag? Now we haven't finished off the CTF, obviously, and we aren't going to because that's not the focus of tonight. But we have written to data on the stack, past the stack canary, and have tricked the program into thinking that a buffer overflow has not occurred. I forget exactly how this CTF was done. I think it was something to do with the fact that there was that's right. I think it was something to do with the fact that there was a limited number of addresses for where this function was stored. So that could also be brute forced, but again, it's not our focus, so we aren't too fussed about it for tonight. So that is the more tedious and harder method to leak a stack canary. There is one more method I want to go through, which is a lot simpler, I think, and that is just leaking the stack canary with format string vulnerabilities. Format strings. So for those, I'll just clear this out first. So for those who don't know, format strings are these like special strings that can be used to specify the format in which data is output. And if a function such as printf is written in an insecure way, we can, as a user of the program, specify how we want our data to be output. And there are some format strings that we can use to leak data that is on the stack. And this is very useful to us because we can then find the stack canary itself. So we are going to be dealing with the same vulnerable program as that Pico CTF one, except that I have modified it a little bit just to include some gets and printf functions. It's just some very simple stuff and doesn't change up the program too much. Just this time around, we are going to be prompted twice to input some data, and the program will print out what we write to one of the buffers. And both of these buffers are of size 32, but that's not a big deal. So if we are to run the program right now, we get prompted to input some data. I'll just put in some non-harmful data for now, AAAA, and CCCC, whatever, and it prints out our data from the C buffer. So I am going to spoil this one a bit as to what the stack canary value is, just so that we can recognize it when we look for it. The stack canary for this one is going to be BBBB. I don't think I've ruined it as far as actually learning about how this works goes. So the way that we can leak the stack is, I'll just put in some A's just for no reason. The way that we can leak the stack is by using the format string %x, and that's going to print out the hex format of that bit of data, so it will show the actual data on the stack. And we could repeat this for over and over for a bit. If I just copy that. Whoops. like so. And so we get all this weird data that we might not fully understand, as well as our, okay, now where's the flag? Now this is printing out data from the top of the stack, and we can actually see the start of our buffer that stores this data here, right here. Because these bits of data are in little endian format, and the hex, look at the ASCII table back up again, the hex value of 25 is percent right here, just like we have here. And the hex value of 78 is, where are we? 78, I can't see, is X right here. And then the hex value of 2C is going to be the comma, and 20 is a space. So that's just me showing you guys that there is a format string vulnerability in here, but we haven't actually leaked the stack canary just yet. There is a particular format string which is very useful for this, which is, what is it? It is percent $n$x, where n is the, where I believe n is the nth value from the top of the nth 4 bytes from the top of the stack. So we could do, let's say, we'll do 10 in this case for no reason at all. $x, and we just get the value 1. Don't confuse that with a 10 because we have our message here. So it's obviously not the stack canary because our stack canary will look like a bunch of 42s since the hex value of BB will be 42 4 times. So if this is not the stack canary, it must be somewhere down the line. But we can use this buffer here to see if we're close, because the data that we are printing out is written on top of this A stack here, this A buffer here, I should say. So if we run the program again, we'll just input a bunch of A's. Actually, let's be more specific. We'll put in, let's say 30. We'll put in, let's say 30. Print A by 32 or 30 this time. These A's. All right, print these, we run the vulnerable function, print in these A's, and then we can put in percent, we'll try 15 this time, $15 $x, and we get 41, 41, 41, 41, and that's not a 0, so that's an O again. And so we can see that we are reading now some part of this buffer here, which means that we're getting close. So we'll try to narrow it down a bit more. Same deal, our A's, and we'll put in our, we'll put in 20 this time, set X. It's still A's, so we aren't quite there yet. We'll try again. We'll try, say, 25 this time, $x. And we get some jumbled up data, which we know is not our stack canary because we know it's BB. So we must have gone past the stack canary. So we'll meet at the middle or close to it. We'll do, try 22, $x. And we get some data that we don't recognize and 4141, which means that we must be very close. So we'll try one more, 23, $x. No, that's not right. 23 $x. And we have now leaked our stack canary for this particular challenge because we have our 42s 4 times. And so like the other programs, I'll just run this program one more time, putting our stack canary in and writing through data on the stack past the canary. So we'll do a Python print, let's say A by 32 plus our canary, which is just the character B 4 times. And we'll include some data which doesn't do anything, but it's just a proof of concept that we can now write past the stack. What did I do wrong? I need -C. Don't I? Is that it? Yeah, cool. So if we copy this data, run the vulnerable program again, put in our payload, and this can now just be whatever. ever we want, whatever. And we do get a segmentation fault, and that's probably because we wrote through some part of the stack that's important, maybe the base pointer return address, it doesn't matter. But we don't throw the stacks matching error here, which means that we have once again tricked our program into thinking that a buffer overflow has not occurred because we haven't modified the value of the stack canary. Now, I think that's just about it. Are there any questions that Marius can read for me?
All right, so the spaceman asks, is 64-bit brute force possible?
64-bit brute force. It depends on how many bytes you're dealing with. Yeah, that's it. Like there probably is some cutoff point. I don't know exactly where it is. Do you mean the entire stack or the same method that I used here? Because if you mean
so the spaceman has clarified 8 bytes.
8 bytes. Well, so we could, like, with the same method that we did, there really is no limit to how long of a stack canary we can brute force. It's just when we're trying to brute force the stack canary's value as a whole, as just one unit, that it's going to take forever. Hopefully that answers your question. Does it?
Spaceman says, cool, yeah.
Cool. All right, cool. Actually, Spaceman, who are you? I gotta know. It's killing me. All right, I think I'll stop sharing for now. I think that I've shown everything I want to.
Anyway,
We'll never know who
I have a
Spaceman
question,
is.
Rafi. So, like,
Yeah, sure.
In terms of like the stack canaries, like how brute forcing it 1 byte at a time seems like that's not like the case in reality.
Most of the time, it is not. It's only really a viable method when the stack canary remains static with each iteration, but or rather with each execution of the program. But each time you re-execute a program, the stack canary is going to change. So the only like real life scenario that I can think that a brute force method would work is in a program that uses the fork method in C, because when you duplicate this process, it's going to have the same data on the stack as it did before. And that's the only time that I think the stack canary would remain constant.
Yeah, thanks. That's a really good point. Yeah, with forking, that would be like, not like a vulnerability, but like something which makes it easier to find the stack canary.
Yeah. It's a pretty, like, if you're connecting to a machine, to some binary remotely and it's using fork, then it's probably going to be vulnerable. Well, it might be vulnerable to getting the stack canary brute forced. I think Live Overflow actually did he did some challenge that was very similar to what I'm talking about right now. Yeah. If you want to look more into stack canaries, or sometimes they're called stack cookies online, Live Overflow, or like just, there are quite a few CTFs that have been done on stack canaries. Pretty easy to Google. Cool.
Right, so just before we wrap up, I'm going to plug MonSec, the Monash Cybersecurity Club. So that's what made this workshop possible. If you haven't already, please fill out the attendance at go.monsec.io/attendance so we can keep doing events like these, because we know you guys are interested. And also, you can give us feedback on our survey at go.monsec.io/survey.
Actually, I want to thank NordVPN for sponsoring this workshop. Go to www.nordvpn.com/monsec10 to get 10% off your next purchase.
This
Squarespace, sponsored by Squarespace. Raid Shadow Legends. We're sponsored by Rage.
Yeah, Raid Shadow Legends. Over 400 champions. Yeah.